Thank you, Michael. As Michael said, I am David Swafford, and joining me a little bit later in this presentation will be Brennan Bennett, both of us from the Facebook network team. And today we're going to be taking a look at how we've been scaling the Facebook backbone and our data centers through zero-touch provisioning. Before we dive into provisioning, though, let me show you a quick view of one of our data centers. This is just one row of our network, one view of our network row in one of the many data centers. And throughout the world, we have 12 data centers announced and 7 currently live. In addition to these data centers, we have a number of small data centers called POPs, or point of presences, throughout the world as well, which you're probably most familiar with because that's where we connect to you guys in the outside world. We operate 2 distinct backbone networks to connect these. One for internal traffic that we cross-connect all data centers together with in a full mesh, and another for the external traffic to cross-connect the data centers and the POPs together. These operate over our own private optical network as well. So as we thought about different problems that we could solve for and things worth kind of attacking, one thing became painfully clear over the last few years. We were turning up data centers left and right, and we had matured quite a bit on the data center side. It was very cookie cutter, everything looked alike, and so we were able to turn up things with minimal pain. In fact, once the data center shell was up, we were turning up the network stack within just a matter of weeks for entire fabrics. But more related to this crowd, what we saw that was a little bit more almost embarrassing is that it was taking forever to turn up each POP, often 2 to 3 months once we figured out a location and so on. The reason being is that we build our POPs in colo facilities with many of you guys as well, and all of those facilities are a little bit different. Different power availability, different physical layouts, different fiber, and so on. And so we picked that problem to kind of narrow in on from the provisioning side to see if we could kind of fix the more complicated situation and make it better for everything. So a small team of us, about 4 of us about a year and a half ago, said, hey, let's go build a POP and see how hard this is and figure out why exactly it's taken a while. Because over time we had grown and been a little bit disconnected from our actual deployment engineers who were doing the real work here. And so we went out to Dublin, Ireland, and hung out in a brand new cage that's being built. And we're just kind of tediously taking notes with our deployment guy. And it breaks out to four common groups of work. We had to build an out-of-band network, an optical network, an IP network, and then finally provision compute capacity. So what's the first thing you might build or bring in when you go to a POP, a new data center, even a new office building? Potentially some sort of internet connection. And that was true for us as well. We would turn up a firewall, an internet circuit, a console server, and switch to both provision the devices over and manage once live to avoid any complicated build ordering. This was all being done by hand as we watched USB keys to upgrade, and then literally copy and paste for the configs, just like old school, with no real common template or anything like that. For one device, one site, not a big problem. As we grew, it was a little bit tedious and error-prone. In the more extreme case, we might bring a POP or data center, or place a POP or data center in the middle of nowhere, and have to bring in optical connectivity. I mentioned earlier we operate our own private optical network, so in that case we would actually have to build out fiber and build an optical line system, which is very much like the network world, where we have devices such as amplifiers, multiplexers, and so on, that are also programmed just like network devices with a CLI interface or some proprietary interface as well. This slide here just shows you a quick view of what a typical POP of ours looks like. Simplified a little bit, but there's a number of layers involved of routing and switching that must all be turned up before the first peering circuit or rack of servers. So as we started to look at this problem, we wanted to pick one of the harder devices to provision and see what was going on and why it was taking so long. As I mentioned earlier, we had a deployment team, and so over the years we had built these large documents that they would follow called methods of procedures, which was simply a checklist of all the items they had to do. So over time, we became a little disconnected on what they were actually having to do to turn up the site. And so for one of our peering routers, the routers that you guys connect to us with, that breaks out to a list like this. In the case of a new deployment, we have to let some people know internally, but in the case of an upgrade, we have to let you guys know, so with some emails and so on. Then we have to do some cabling, some physical work, assigning IP addresses, generating config, and so on. Now, being Facebook, we're very software-centric, so some of this was already automated. Things like letting people know. That was a CLI tool that a user would run, or a deployment engineer would run, and it would post in a Facebook group or send an email. Things like config generation were also automated. Not by one tool, but by 3, but still automated nonetheless. Even the act of placing production traffic onto a device, which is generally just changing BGP policy, that was automated by another tool as well. Now you might ask, why is this a problem right now? We have this large document, it's very structured, tells the deployment engineer exactly what to do. The problem is that we had become a little bit disconnected from the pain and the amount of effort it was taking them. And so what we saw is that just for a peering router, it was 30 steps, 10 different CLI or UI tools. And unfortunately, those tools were written by different people over different periods of time, and they all acted and felt different. Now, it wasn't just 10 tools for the entire site, though. We had a number of different roles of routers and switches. And so we saw 100 to 200 steps on any given build, with maybe 15 to 20 tools. Now, this picture here is also another visualization of things that the MOP was not helping fix for us. So we had an outage where a new guy had joined the team, and there was a step that was not written down in the MOP that everybody just kind of knew and had in the back of their head. And so he didn't know about it, and he skipped it. Unfortunately, that outage caused a bit of a traffic impact to those users in that POP. And when we looked at the outage in something called SEV review, where we were like, hey, what happened, trying to dig into the root cause, we're like, oh, you skipped a step that was not written down. Well, we can't really blame a guy for skipping a step that's not written down. So our takeaway was to write down the step. Unfortunately, 2 days later, in the same POP, another maintenance on another router caused the same outage. This time by somebody more experienced, who knew exactly about that step and everything, but it was 2 a.m., and he wasn't reading them up because he had it memorized. That's an example of why writing things down in giant MOPs were not really a solution that we wanted to keep around. So as we thought about trying to solve this, we had some software, we had some processes, but we wanted to kind of think, what if we started over? Specifically, we wanted to build a solution that would let us automate this entire process of building both a POP or a router or a switch with a push-button experience. Imagine walking up to either an arcade game or a vending machine and typing in a couple button presses, and out comes a provisioned router or switch. Eventually, a provisioned POP. So while that might sound like made up and like magical and all that, that is in fact what we built and what the rest of this talk is going to focus on. So as a small team of 4, about a year and a half ago, we were trying to look at this problem, and we huddled up in a room with a whiteboard, and we're like, let's start breaking this into pieces. One major piece that we needed is that we needed a way to reliably apply configuration and code to a device. We had a console-based system, but it wasn't working very well. We also had some software already for notifying people and checking hardware and so on, but we needed to potentially rethink and start over and just throw away and start fresh with more integrated and better software. But one final point that we kept close all along that made this project successful is that we wanted to empower and enable our peer network engineers and our deployment engineers from the beginning. So we were on a team of 4. We were network engineers working mostly on software, but on the network team, trying to solve this problem, but we did not want to solve it in isolation and be like, hey, 6 months to a year later, here you go, it's all done. Hope this is what you wanted. Instead, we recruited people from both the backbone teams, the network, the data center teams, even the guys that were in the field to help us along the way so that we would know what we were building was what was actually needed. And specifically to have them help us build it so that as we got further in, we wouldn't miss things and we could keep the problem and the pain close to us as we try to fix that. So as we step back a minute though, so looking at the first puzzle piece, we needed an option to apply configuration reliably. So one option is shown here. Who here is familiar with what's on this slide? Yes, expect or p-expect based scripting. Where you pretend to be a human with scripts and you type over the prompt and you do a lot of regular expression matching and try to craft things like the enter key and so on. Now what comes to mind when you think of this? Is it joy or is it tears? Okay, cool. So depending on your evolution in the programming like life cycle, this is generally the first thing you step towards as you automate things. In a way, it's really cool because you can suddenly be a little bit lazy, which is what we all really want. And that is a great goal to have, because now you have software typing for you and interacting with these prompts. The downfall to this, though, is that you're not really writing software so much to write software, and you're not really building networks to build networks, but now you're building software to pretend to be a human. So you have to build a lot of intelligence and error handling about these prompts, and you have to always be able to be at the right prompt, for example, and craft things like the enter key. One problem, and we had a system based on this for a while, that was causing a lot of heartache. Specifically, the heartache we were having is that our workflows have become so long in the data center side with these console systems that we would have 2 or 3 reboots involved, and we might have to do firmware upgrades multiple times, depending on the steps involved. And so if you wanted to change something after the first or second reboot, well, you had to go erase a device, run your workflow, reboot the device twice, get it to that point where it's ready, and then now hope that you don't crash while you're testing your change. It led to a lot of time wasted, and so we wanted to think, what if there's another way that could be better? So another way we could look at is what the server world has been using for decades now. Pixie boot, or specifically DHCP, so in the server world, Pixie boot. Even the network world has this, more recently through Zero Touch Provisioning, but even back in 2000s, we had a method with THCP and broadcast-based. And so that's actually what we adopted, and we're going to go into this in more detail in just a bit. So this picture here is just a visual of our mission early on. We wanted to automate this experience of building the more complicated devices with that of walking up to a vending machine. This is one of our vending machines from Facebook where we can walk up to it, swipe a badge, and get IT supplies such as batteries or a charger. So as we think about the picture, I mentioned earlier that one part of it was configuration, so potentially console or zero-touch provisioning. But there's a lot of other pieces needed to fully provision a device. For example, who here has documents like I showed earlier where it's a large checklist or a method of procedure in your environment? Do you like those? Okay, cool. This gentleman up here is shaking his head no. So we wanted to get rid of those. So looking at that part of the puzzle, we needed to write a lot of code to automate all of those checklist items. We also needed a way to organize that code and build workflows that were specific to each role or device that we were building. And finally, we wanted to specifically build it in such a way that we could replace these mops with a button or a command. So that is what we did, and how we did that is by choosing to divide and conquer. We realized early on that as a team of 4 working on the network side, trying to focus on provisioning, we were not large enough to fix everything for all of Facebook. But we also wanted to keep the problem really close to the guys that had the pain. So what we did is we recruited people, and specifically to do that, though, we built the system with them in mind. So we focused on our deployment and network engineers and made the system structured in such a way that they could be onboarded very easily without much overhead. Specifically, we wanted to remove the barriers. No longer did somebody need a computer science background to understand how to change a few lines of code or to change parts of these provisioning systems. And in doing so, we wanted to empower them so that no longer would they have to put in a feature request or file a bug and ask and hope it could get on somebody's roadmap or get some software engineer to work on it, which, no offense to software engineers, they're great as well, but they need to, in our environment, we wanted the peer network engineers, the deployment guys, to be welcomed and have the freedom to make changes in the system. So as we talk about building for the network engineer, the way we did that is we structured it so that we had small, independent pieces of code that could be written in any language. So if a guy had a great bash script already, we wanted to allow him to continue using that in this system. If they knew Perl or Python, we wanted to allow those as well. We didn't want to add the overhead of forcing learning of another programming language, whatever we chose, to get into this. We also wanted to make sure that we kind of enforced the Unix and Linux philosophy of doing one thing and only one thing well from the individual portion of the workflow. But finally, we wanted to make sure that those working on this problem, the deployment and network engineers that know MPLS and BGP really well, but maybe not so much software, we wanted to make sure that they didn't have to understand the entire system to be able to help us with this problem and write their, for example, their BGP check or their step that does undraining of traffic. So in the system, when I talk about isolating the system or keeping the knowledge separate, The way we did that is we called units of work steps, and a step is simply a compiled piece of code that is executed as a binary. In doing so now, we only have to test and develop that specific step. No longer does one have to run the entire workflow or get a device back to the console prompts that one at the beginning might expect. So the system specifically is named vending machine. It was a purpose-built workflow automation system that we created on the network team, created specifically around zero-touch provisioning. And around is a very key point here. So as we started looking at the zero-touch provisioning solution, one thing we noticed is that it was great for applying configuration and code, and the devices would self-provision themselves, but then we lost some visibility, and we're like, well, what devices are provisioned? What devices are provisioning right now? What devices didn't really even start because something wasn't plugged in? So this is where we got to with those MOPs on the peering router, for example. Everything except for rack and stack and cabling has been automated. For those, we're still waiting for some robots from Amazon, but the shipment's a bit late. But for right now, we have VM configure as a command line that the deployment engineers run that runs all of this. So enough about the background. Let me go a bit more technical here. So zero-touch provisioning is a name that is a quasi-standard across a couple of the vendors right now, which is just a method of provisioning a device from a factory blank state using DHCP. So while factory blank, a device that supports this will send a DHCP message over its management port or potentially over its uplinks, depending on the vendor, and it encodes something, the option of option 60 for vendor class with a string that contains the vendor name, the model number, and the serial number. The serial number here is significant, though, because it allows you to react differently or uniquely to this request on the DHCP server based on who is asking for the configuration. So in our case, we already know what serial number is what device, specifically what name, based on the mapping of our inventory and receiving system. And in doing so, you could respond differently from one device to another, or choose not to respond if you want to kind of gate or control what devices are allowed to provision. So in the more simple case of zero-touch provisioning, that's across most of the vendors that support it today, the simple case expects a response of a config file. Another option is a list of files where the config file and the firmware image are encoded in this response. A third option that several of the vendors also support is responding back with an executable script in one or more languages. So in our case, we respond back with a script, which is simply an HTTP path that the device sees and then downloads. We provide that HTTP web server that responds back to the device, and then it starts executing that script. So you might ask the question, if zero-touch provisioning can load both the configuration file and the firmware, and generally, also that triggers upgrading the device and the device self-reboots, why would we respond back with a script? So in our case, we wanted to have better visibility and connect and build a feedback loop. We learned of this problem actually just after going to one of our data centers, also in Ireland, about the same time. And we're like, hey, let me watch you build this network using zero touch. And our deployment guy is like, cool, I have 64 devices to turn up today. We just got power, but they've been racked for weeks. He's like, okay, this is working. How do I know it's working? What do I look at? And we're like, build a script, ping them. I don't know. And we didn't have a very good response. And the guy's like, well, no, I don't want to do that. And so then we were like, we went back to the drawing board a little bit, and we're like, okay, cool. Well, let's have the device tell us when it started and when it finished. So we built a script, and the device basically downloads the script in response to that DHCP message. And the first thing it does is it makes an HTTP call to our service, vending machine. It says, hey, I'm starting, and here's the serial number. In our case, we already have a job kind of pre-staged based on devices coming in, and we're like, okay, cool. This is job number 5, and 5 is now moved into running or active. The other part that we did with the script is that as part of provisioning, we have to download one or more files. For example, the firmware, the configuration, maybe some other scripts that we run in the box. And so we have the script logged to us remotely, what files it's downloading, and when they finish, which helps us a lot in troubleshooting because we have some really overly protective security guys that change firewall rules all the time. And so they break provision, probably once a month right now. with different firewall rules. But now, because we have these log messages, we can kind of see, oh, this device tried to download from here. That didn't go through. Let's go check firewall rules, or let's check routing, for example. And finally, the device tells us then when it's done, which now lets us signal and start other things in response to it without anybody kind of having to babysit or watch it. Now, this was great at all at first, but it introduced some race conditions that we saw. In our case, we do not predetermine the management address or that out-of-band management address ahead of time, because it's, well, specifically in the POPs, because it's based on where things are plugged in, and the layout is different for each of our POPs. So we kind of let it go freeform, where like just plug in any management switch, any port, and then we'll assign on the fly. So we did some hooks on the DHCP process where we parse option 82, which in the ISP world you're probably familiar with, which passes on things like the physical port and the VLAN and the switch. And we assign the address in real time. But that means we have to generate configuration in real time before we try to load the configuration. So in doing that, we realized we needed a way to delay zero-touch provisioning from running on this device without breaking it. So the way we do that is that we shimmed into this HTTP web stack where the device tries to download the script. And we're like, OK, I see your device X, because it passes the serial number on the request, and you're trying to download this script. Are you allowed to download this script? And so we check and look at the job. And so in this, I'm trying to visualize. We have three steps that I have to run before zero touch. 2 in green have completed, and 1 in white is still running. So the one in white, we want to guarantee that it completes running before we start zero touch. So in this case, we will raise a 404 not found message or error back to the device and basically crash its DHCP or its process here of trying to zero touch. The vendors that have implemented zero touch basically do failure handling in an infinite loop where they're like, OK, something happened. Let me try again. New DHCP request, new attempt to download. This lets us buy some time and then guarantee that other steps have finished before we respond back with the agent. Once we give the agent back, this is just a view of kind of an actual workflow where we have different groups that run 1 or more steps either in serial or parallel. In this case, a workflow showing where we rebuild a device, so we erase it before zero touch. This is just another view here of things that might run after the device reboots. So we check on things like, are you up yet with trying to SSH in and run some commands? Are the BGP peers up yet as well? Because we're doing this over management, so we don't actually know if the uplinks work until we check on those. And then finally, we just automated the act of undraining or placing the device into production as part of this workflow. Now, that does take basically some confidence in your tooling to know that it is safe to put in production. But once you get to the point of building enough checks and enough verification, then there's no point of delaying or making that manual, and so we just build that into it. So stepping back a minute, when I talked about simplifying and building for the network engineer, what we eventually got to is a point where our team of 4 had 30 more network engineers working on this problem across backbone, data center, and deployment teams helping us. It was a little bit crazy to think about it, but we actually have provisioning now for optical devices, for power strips, for all kinds of devices. And it was only in response to all these people that just kind of joined us and helped us. This is a quick view of what exactly they're writing so that you can kind of see how we simplified this. So when I talked about a step being a compiled piece of code, this is an example with Python. All of our steps have some basic boilerplate that they implement under this function of main, these first 3 lines, where we parse input over standard in as JSON and decode things like the host name, the serial number, the job number, and provide that data in a simple interface to the step. And so this is an example of generating configuration, which has 2 methods, build configs and verify configs. And this is just an example of some Python code making a thrift request to a remote server and saying, hey, go build this configuration for me, and waiting for the response. And then finally, just another example of verifying the configurations, just to make sure that, yes, we are able to download them the same way the agent might download them. This is another view where we pass in, again, that JSON string to the step. So as we run the step over the command line, we literally echo in the string that has the metadata that it needs. And then logging is sent to standard error, and we just capture that and expose that with the job message, or the job. The result of this step is just sent to any machine through Linux exit code, so we just signal success or failure. And with that, I'd like to welcome Brendan Bennett, who's going to dive into more of the details of how the back end of vending machine works.
Excellent. Hello. Excellent. Well, thank you very much, David. So I want to talk a little bit about the back-end details of vending machine and some of the decisions that we made along the way. So to start off, 4 of us got together and we started looking at, if we had to do things over again, how would we do things differently? So first of all, the system had to be very flexible and support rapid deployment. So multiple engineers need to be able to work on the system at one time. So how do you organize, one piece of code that everybody needs access to? The system also needed to be extremely scalable and fast. So Facebook is building tons of data centers. We're building tons of POPs. We're constantly refreshing the network. So it needed to be extremely fast so that engineers weren't waiting on the data centers or the POPs to be built. And it needed to be scalable so that we can run multiple of these jobs at the same time. It also needed to be very resilient. Building any distributed system or interacting with any distributed system, things go wrong, and you need to be able to react to that. And then finally, it needed to be predictable. When a deployment engineer types in a command on the command line, they should know exactly what's going to happen. This kind of gains confidence into the system. So here is a very high-level overview of the system. We took the system, we split it into 2 separate parts. We have the controller, which is kind of the hub of the system, and the executors. The executors are nothing more than a dumb worker queue-based system. Tying these 2 pieces together, we have a MySQL database, which you can see here on the left. The MySQL database keeps state about the system and allows us to build this out distributedly. And then we used a Zookeeper-based queue. So this is Apache Zookeeper, and it allows distributed consistency across multiple systems to work together. And we built a queue based off of that. And I'll talk a little bit about that in a second. So the controllers are responsible for 2 things, really. The controllers are API into the system. So if any other systems need to interact with this, it goes through that controller. It is also our VM CLI client that the engineers work with are nothing more than an API client into that API server. We use we use Thrift for this, which is very similar to Google Protobufs or gRPC, if you're familiar with that. The other part that the controller actually handles is queuing, actually taking the steps, finding out what steps to run, and queuing them into the Zookeeper queue. So this is an example of what the queue looks like. So once the controller decides what steps need to be run based off of what device we're building, we add it into this global queue. As additional jobs are running at the same time or additional steps need to be queued at the same time, they get added down to the bottom. So we pop from the top of the queue. So it's very simple from that point of view. So an executor, when an executor is ready to handle some work, it will first take a lock against the item in the queue. We take a lock just in case something happens to that executor. We don't actually delete it or pop it from the queue. We want to make sure that it stays on the queue, but we lock it so that no other executor can touch it. The executor then, at that point, will go out to our repository and download the latest version of whatever step it's running. As David mentioned before, each step is its own contained binary or contained script. And so this allows our engineers to actually write asynchronously, if you want to think of it that way. So our engineers can write their steps, publish them to this repository, and we'll always fetch the latest version. We don't have to redeploy the back end, and we can have multiple engineers work on different parts of the system at the same time. So once we've pulled down that latest version, the executor will then, as David mentioned before, take a JSON payload about the metadata of the job and pass it into that step via standard in, and then that step will report logs and other status information across standard error. Finally, when it ends, the executor will look at the exit code of whatever step it was running, and in the case, and report that back to the controller. In the case that everything's fine, the controller will then queue the next group and the next steps that are available. If something went wrong, for example, the controller will actually requeue the entry. And you can actually see here circled in purple we requeued the entry as a brand new entry. We popped the original one, and we do this to prevent head-align blocking. So that functionality that we just talked about, it's called retries. And it's very important when working with a lot of different systems in a distributed environment like I talked about before. So it is very common for something to go wrong, especially when you're doing many of these jobs. So if something goes wrong, for example, a server that crashes, usually there's some system to help you redirect to a different server and your next request will work fine. Here at Facebook, this happens quite a bit and we got very used to doing it. So we have something that we call retryables. Retryables are nothing more than a block of code that we put a little decorator around or some sort of logic around it to say, go ahead and retry this X amount of times and wait X amount of minutes or seconds in between the tries to have some sort of back off so we're not just hammering or making the problem worse. This is really great, but what we found is that because there's so much different code written by different people, that retryables sometimes aren't thought out throughout the system. We had an example of a piece of code in NetEdge that had a retriable around it. And inside of that block of code, it called another function that had a retriable around it. And it, inside of its block of code, called another area that had a retriable around it. So if you actually think about this, there's retries happening on the most inner function. Those will, let's say it's 5 times, so we'll retry that 5 attempts. It will fail. It will bubble up to the next retriable block of code. That failure will bubble up. Will fail there, and it will then retry that inner loop again 5 more times. And then you repeat this up until we have the 3 layers of indirection, and it was taking 4 hours for this piece of code to fail. So we wanted to fix this in vending machine, and we did it based off of this requeuing logic. So by abstracting it outside of the step itself, engineers no longer had to worry about figuring out this retry logic themselves, and we could expose actually what's happening down to the end user so they know exactly what's happening, what's going on. The other thing about this is we actually abuse this system. One of the things that happens directly after we do the ZTP step is that the router reboots with brand new code and brand new config. So we have to poll to see when that router is actually up and reachable. So we do that via a simple SSH connection. So we'll SSH into the box, and either the socket will be down or the system's just not ready to accept an SSH connection. Instead of actually building the logic on a loop inside of the step itself, we simply have the step fail. So the step is a very simple code. The step fails, the system requeues it, and we try again. So it's very common for us to build steps that fail on purpose because we know that we're waiting on some sort of external state. So we've talked about steps a little bit here. I want to talk a little bit about how we know what steps to run. We have a lot of different devices at Facebook. We have our data center equipment, we have routers and POPs, we have optical now, and we're now just onboarding power gear that's going to be deployed via vending machine. So how do we know each one of those has different steps and each one of those has different requirements, and that was designed as part of the system. So how do we know which steps to run? So we call that target selection. So target selection is actually a pretty simple concept. We take a device that has attributes on it, so we look in our back-end inventory system. We look at that device and we have a number of targets. A target is nothing more than having those exact same fields and doing some sort of string or regular expression matching against those fields. So here we have a simple example of a device, a Wellfleet device, actively used in our network. And we have a bunch of targets off to the side. So we can see the first target here is actually matching one of our wedge-based devices, one of our self-built top-erect devices, so it's not a match. We step through the next target, and this one actually matches on any serial number, any model, any location, and specifically Wellfleet. So this is a match, but just like a routing table, we look for the longest match. So we'll continue through all the matches, and we'll actually look to see if there's anything more specific. This one is matching on the location of Denver. It matches on 2 fields. The previous one only matched on 1, so it is the most specific. So once we do a match, that target has associated with it exactly what needs to happen. We have many different job types in the system. Here we have three that are our most common three. It is configure, reconfigure, unconfigure. So configure is simply bringing a fresh box into our network, kind of the traditional provisioning sense. Reconfigure is taking an existing box, pretty much wiping it and treating it like we're going to rebuild it and get it back into a well-known state. We actually do this quite a bit just to deploy software and code and changes. And then unconfigures are RMAs, decommissions, anything else along those lines. Each one of those have different steps, and so the target itself defines what steps need to be ran. We also define groups of steps. So if we have a group of steps, or for example, those 4 boxes next to each other, they're actually ran in parallel. So that's how we get a little extra speed out of the system. Is there's certain things like updating some backend database, maybe updating DNS. These things don't rely on each other. So we can actually run these steps in parallel versus having one wait after the next one serially. You can also see here that we're able to utilize steps in multiple different locations for multiple different devices. We just compose them differently based off of what the target is telling us. So everything we've talked about so far has been focused on a single device. And as we were building vending machine, we actually realized that as network engineers, we don't work on single devices. We usually build a pod of networking equipment. We rebuild a data hall. We decommission a POP or a rack or something along those lines. So we needed to, we looked at this, and vending machine could adapt itself to actually work in this same context. So the idea is that we're able to take a job and run it as a step in a parent job. So I'll talk about a quick example of this. We have a network called Express Backbone. If anybody's familiar or has followed us, Express Backbone is a purpose-built, internal backbone that we have, but it's actually not one backbone. It's actually 8 parallel backbones. We call those backbones planes, and they mirror each other, but they're actually not connected to each other. So we have 8 planes that work in between all of our data centers. A typical way that a network engineer would go about rebuilding this area, or this, this backbone, is they would go and drain the entire plane. So we can take the traffic off at one entire plane, the traffic sheds onto the other 7 planes, and then we're able to work on that plane. Vending machine would then be used to rebuild every single box inside of that plane. We would verify everything's fine, and then we would run a command to re-advertise BGP and undrain that plane. We then repeat that 7 more times for the rest of the planes, and we do this on a weekly basis now. So we looked at this and said, well, just like how David destroyed the MOPS for building one box, we can also destroy MOPS for building multiple boxes. So now vending machine, we can run steps, or run subjobs as steps, and those steps are ran as just regular, those jobs are just ran as regular steps. So we are able to automate this entire system together. So here is a couple CLI outputs of what the system looks like, or what the deployment engineer actually interacts with. To start a configure job, you simply issue the VM configure router command, and you'll get back a job ID. This is a VM detail command. You do VM detail on the job ID, and you get information about the job itself. Here you can see we have a status bar that shows how many steps have been done. We have the status of the job, as well as when it was started. And then we have a list of all the steps that get ran that are kind of blurry and hard to make out there. There's a couple columns that I think are kind of important that we expose back to the user. So one is the ATT column. That stands for attempts. Attempts are how many times we retried that job. So we can actually see like what attempts are not working correctly. We will fail the entire job if we hit a max. Here all these attempts are set at 30, so a very high number. And you can actually see 5th item down, I think that is. We actually had a step that took 6 attempts, but finally passed. The other thing that you can see is the G on the left-hand side. That G stands for groups. So anything that shares the same group number runs parallelly. So we can actually see there's a bunch of 4 steps there that start with 3, and they have start times of around the exact same time. So we're actually able to speed up the development or the deployment based off of running those in parallel. To get more information about what's happening, we have the VM log and VM log tail commands. This simply scrapes the database and looks for all logs coming from every single step, as well as the ZTP process itself. So this gives us a debugging point of view, and also gives the deployment engineer a view on exactly what's happening inside the system. So why did we build the system? You may be asking yourselves. So it was 4 engineers that got together, and we decided to see what we could do. To be honest, we didn't think we were going to build a system. We kind of just talked about how we would do it differently, and we took that into doing a prototype at one of our hackathons. That prototype kept growing, we kept iterating on it, and that turned into a system. And then eventually we called that system a vending machine. There are features like job on a job that we didn't even imagine when we first started building the system, but it came apparent through actually building it ourselves. We also were able to empower the engineer. There is no way that the 4 of us could have wrote every single script to build every single one of these devices in every single one of the iterations, both role, make, and model. There's a lot of things that need to happen, and we couldn't do that ourselves. So by going with a step approach, we're able to empower engineers. And finally, we're able to just control our own destiny. We were able to build a system for us, and it works great because of that. And with that, any questions? Thank you.
Yep.
So I'm Margaret Kiyoshi from Huawei. Okay, so I've operated networks before. So my first question, see if the second question makes sense, is do you have a maintenance window where this is time-bound?
We do have maintenance windows, but we don't, it's up to the engineers to figure out what those maintenance windows should be.
So as your network gets larger and larger, do you have an analysis that says, I want to do all these upgrades or whatever in a certain window? So do you have an analysis that says, okay, to simulate, say, yes, I can fit in that window, or no, which means, of course, you can't fit in that window, then of course you got to modify or change or add more buffers or whatever.
No, not yet. So that's something that we're definitely working on. We're not too concerned about windows. We really rely on our engineers to figure out, hey, just do the right thing, right? So we're less worried about the actual time when things get done, but what we are worried about is 2 engineers trying to work on the same box at the same time. And we're trying to solve that via locks. But for the most part, we allow engineers to make smart decisions and do the right thing. So
another question, more about security. Do you allow any box to get on your network? Is there any kind of authorization? If I walk in and bring a box, put it in, does it just get provisioned automatically?
Yeah, so that's a really good question. When we first started this, it was self-triggered. So originally we were like, any box trying to DHCP, we'll automatically try to provision it. Security was a thing in mind, but the bigger problem was we lost visibility with what was being provisioned and devices randomly doing it on their own. So we did lock that down. Specifically, we have every device or every serial number in an asset management database that contains data about the location and the serial number and the name. And in that, we have a status field that is either in use, received, in shipping, and so on. And so specifically on our DHCP server, which is just the open source ISC DHCP Kia service, we have hooks in that where we write some custom code, and it basically parses that request. And that's actually part of why that serial number is very important. Some of the vendors forgot at first to put serial numbers and things in that string, so we'd asked and gotten that added. Because we use that serial number to check that database and say, is it in the proper status? And if it's not, we just ignore the DHCP message and just throw it away. And so that status gets changed as part of starting the job from that VM CLI.
Okay, so there's no real key encryption security or anything. It's just a serial number, because that's pretty easy to guess, right?
Right. But it does kind of enforce that someone has to have changed that status, which does have its own restrictions on who can run these commands and run these CLIs. But cool. Yeah.
Security on your management network is still very important. So that kind of is, dynamic ARP inspection, DHCP inspection, et cetera. So that still becomes very important. Cool.
Go.
Thanks.
Thank you.